My name is Malcolm McClure, and I would like to present an idea that I had regarding quantum mechanics. About 25 years ago, it occurred to me that simply by expanding our understanding of space a little bit, we could create a model of quantum mechanics that was entirely intuitive, or at least almost entirely intuitive. That is to say that all of the weirdness that we associate with quantum mechanics would simply fall out naturally from the model. Now, I have a strong enough physics background that I understand what I just said sounds preposterous, that it sounds crackpot, and frankly, I would be inclined to think so too, except that every time I go through this model, it just works so well. It just has the right feel to it. So I thought what I would do is present it here and leave it to you, the audience, to be the judge. So let's get started. Now, the model of space that I'm going to propose has three-dimensional elements to it. First of all, this model contains one time dimension. I haven't got any particular insight as to what time is, and so when you see time in this model, just assume that it's plain old t that you're used to from physics and math problems. Next up, there are three extended dimensions. And by extended dimensions, I am referring simply to x, y, and z, again, what you're used to from math and physics problems. I have added the word extended here simply to differentiate this type of dimension from what comes next, because this model also contains 6 collapsed dimensions. Now, I'll explain in a moment what I mean by a collapsed dimension, but for the moment let me just point out that this model then has a total of 10 dimensions in its space-time. It's a 10-dimensional space-time, and that I'm intending that all of these dimensions are fully orthogonal to each other, even though it may not appear that way as we start seeing some diagrams as they come up in a little bit here. So what do I mean by a collapsed dimension? Well, as I go through this, first of all, it may sound like I'm talking about string theory, but very quickly you'll see that's not what I'm talking about. Let's imagine that in preparation of this discussion, I've taken a large sheet of paper and rolled it up and stuck it in a mailing tube and left it there for, say, 6 months. Okay, now in order to explain what I mean by collapsed dimension, let's take that paper, roll it out flat on a desktop, and put coffee cups around the perimeter to hold it open, and look at what we've got. We'll see a two-dimensional surface where both dimensions are equivalent and interchangeable, and there's nothing particularly exciting. But to denote this fact, let's draw on the paper a coordinate system. We'll make one dimension in red and one dimension in blue. Now, if we remove the coffee cups, things begin to get interesting. The paper, of course, coils back up, and we find that our two dimensions are distinctly different from each other. The blue dimension hasn't changed. It's still an extended line, and every point on that line is separate and distinct from every other point. But our red dimension has coiled back on itself, so that if we traverse along this line now, we're covering the same points over and over again. All right, so far this sounds like string theory. And if this were string theory, I would suggest that the size of our roll has reduced to on the order of the Planck length, 1.6 times 10 to the minus 38 meters. But I'm not going to do that. What I'm going to suggest here is that the coil shrinks all the way to 0 size, so that the red circle collapses down to a single point along the blue line. Now, it's this red point that I'm going to refer to as a collapsed dimension, and they will have certain properties which we'll now delineate. First of all, as I just said, collapsed dimensions have a quiescent size that is 0, but they're elastic, that is to say they can be stretched open, and we'll see why that's important in just a moment. And finally, there are actually 2 collapsed dimensions embedded in each point along an extended axis. You can see that in the diagram here in the center illustration. Off to the left side there, you can see that as this coil is rolling up, there's actually 2 dimensions that collapse into the single red point in the bottom diagram. Now that we've talked a little bit about the background space, let's turn our attention to particles, because how the particles are embedded in this background space is what makes this model work. So let's take a look at electrons first. We are going to make the rather audacious assumption that an electron is a 3-dimensional object, but that the 3 dimensions that an electron inhabits are all collapsed dimensions. and as I'll show you in just a second here, that endows an electron with some rather interesting properties. First of all, where an electron exists, the collapsed space has to be stretched open to accommodate that electron. I've tried to depict that here. I've shown two collapsed dimensions and one extended dimension, the collapsed dimensions being in red and the extended dimension in blue. The black disk in the center of the diagram is supposed to be an electron, and here I've shown with the arrows that the space has to be stretched open to accommodate that electron. Obviously there's a third collapsed dimension which I can't depict in this picture. Anyway, because of that, we would find that an electron has a certain intrinsic energy associated with it. That is to say, because the space is stretched open around it to accommodate the electron, if you could somehow or other annihilate that electron, the space would close up and energy would be released. And I've tried to depict that in this diagram. Here I've just simply turned the arrows around. But what this is supposed to show is that collapsed space is constantly pushing in on the electron. Next, we would find that electrons would appear to cling to the axes of extended space. It may not have been clear from the way I described this earlier, but if you look at the diagram here, what I've done is, assuming we could figure out how to manipulate an electron and push it off into collapsed space, in principle we could do that, but the forces would then be increased on one side of the electron and so would tend to drive it back on axis. The forces will only be balanced on this electron when it's centered along an extended dimension. Which brings us to the next property. Electrons would appear to us to be point particles. Because the electron has all of its volume in collapsed space and none in extended space, when we as good physicists start probing an electron to figure out how big it is, we can only probe it in extended space and it would appear to us to have zero volume. It would appear to be infinitely localized. I've tried to depict that in this picture here. Again, we've got the disk that has its volume only in the collapsed dimensions, the two red dimensions, and nothing in the extended dimension. We would be able to perceive the existence of that electron at the place where the extended axis goes through the center of the electron, but the volume of the electron would appear to be zero. And that, of course, would lead to all kinds of problems in our mathematics because we would have to assume that an electron has infinite charge density. The next property we would observe is that electrons would appear to have a certain ghostly nature to them. In this diagram here, I've depicted, again, an electron that's been pushed off axis. We'll talk later about how that might happen. But of course, that means that there are going to be collapsing forces trying to drive it back on axis. But what happens when it's temporarily off axis? The electron would seem to disappear to us. It would seem to vanish momentarily, but then show up again. So this model supports both conservation of charge. The electron always comes back on axis, but it may momentarily disappear. And so the electrons, as I said, would have this ghostly nature to them. And there's one more property that we might expect electrons to exhibit in this model. As I said, an electron is three-dimensional, but the three dimensions that it inhabits are collapsed dimensions. Well, since there are 6 collapsed dimensions available, it would be possible, at least in principle, to take a second electron, and as long as it's oriented non-coaxially with the first electron, we could put the 2 electrons in the same place in extended space at the same time. 2 and only 2 electrons. But as I said, the electrons would have to have this strange oppositeness to them. And what I'm suggesting by this, of course, is the Pauli exclusion principle. And so I would associate in this model the idea of spin up and spin down as being oppositeness in collapsed space, in other words, non-coaxialness of these 2 electrons. Let's set electrons aside for the moment and turn our attention now to quarks. First, we'll start with an assumption similar to that we used with electrons, wherein we said that an electron was a three-dimensional object, but that all of those dimensions were collapsed dimensions. Let's assume that a quark is also three-dimensional, but in this case, a quark inhabits 2 collapsed dimensions and 1 extended dimension. What kind of properties would that endow quarks with? Well, first of all, invoking logic similar to that we used with the Pauli exclusion principle, we would find that quarks would be able to group together in groups of 3, but that in order to do so, they again would have to be non-coaxial. In other words, you can't have interference between the dimensions that these things reside in. And so you'd find that this group of 3 quarks would reside in all 3 of the extended dimensions plus all 6 of the collapsed dimensions. My guess is that this non-coaxialness, this non-dimensional interference, is what we interpret as color neutrality. Next, notice that these baryons, clearly that's what we were talking about, that are made up of these 3 quarks, take up space not only in the 6 collapsed dimensions, but also in all 3 of the extended dimensions. And so as we start to probe these things in the 3 dimensions that we're aware of, we will find that they have actual volume. They're not point particles like electrons appear to be. I'm going to finish out this section on quarks with a little hunch. Since quarks are made up of 2 different kinds of dimensional elements, namely they have 2 dimensions that are collapsed and 1 dimension that is extended, they have the ability to exhibit chirility, that is handedness. And I think ultimately we will find that up and down quarks actually correspond to left and right-handed configurations, though perhaps not in that order. And a further hunch would be that in order to pack quarks in most efficiently into collapsed space, in other words, you stretch collapsed space by a minimal amount, we're going to have to pack them in as 2 ups and a down or 2 downs and an up. But if you tried to do it, say, 3 ups, that would stretch collapsed space to a greater extent and hence be unstable. The next obvious step would be to take our electrons and baryons and start building atoms out of them. We'll do that in just a moment, but first I'd like to take a couple of minutes to talk about tunneling. So I ask you now to consider this diagram. Here what I've represented is a 3-dimensional cross-section of 9-dimensional space. And so the 2 of the axes are labeled. One you see as an extended dimension, the vertical one is a collapsed dimension, and then where the blue arrows are, that's also an extended dimension. So we've got 2 extended dimensions, 1 collapsed dimension. The green circles represent atoms. And so what I'm trying to depict here is an atomic barrier that is 2 atoms thick along the blue axis, and obviously many atoms along the other extended axis. And these atoms protrude a little bit out into the 1 collapsed dimension that I'm showing here. Now we have a beam of electrons, shown as red dots, that are being fired toward this barrier, which is 2 atoms thick. I've depicted most of these electrons as being along the blue axis, because if you'll recall, electrons tend to be driven back onto the extended axes. They tend to cling to those axes because the collapsing forces drive them there. The collapsing forces I have depicted by the 2 black arrows. So most of the electrons are shown on axis. A few of them are shown off axis because, as I also said earlier, it is in principle possible that an electron could get pushed off into collapsed space, but momentarily will be pushed back on and reappear as far as we're concerned. So what happens when these electrons hit this barrier? Well, the ones that are on axis, the vast bulk of them, will either be scattered off the barrier or perhaps absorbed by it. But a few of the electrons that may be out into collapsed space at that moment have the ability to pass right by the barrier. The collapsing forces then drive them back on axis on the other side, and voila, it appears that the electrons simply tunneled through the barrier. What does your common sense intuition tell you should expect from this model? Well, 2 things. First of all, the number of electrons that can tunnel through the barrier will increase if the barrier is thinner, because obviously the electrons have to spend less time out in collapsed space. Second of all, if you increase the velocity of the electrons, you will get more of them tunneling through because, again, they will pass by the barrier quicker. And of course, both of these are in accord with what we actually do observe. So let's now set about the task of building an atom out of an electron and a baryon, which is to say a proton. I haven't talked any about charge yet. We'll do that in a few minutes. But we already know that an electron is negatively charged and the proton is positively charged. So there'll be an electrostatic attraction between the two. So the problem we're going to propose is very similar to the standard freshman exercise of bringing two charges together from an infinite distance. And I've tried to depict that here. In the center of the diagram, you see a green circle, which represents the proton. And off to the left of the diagram, along the blue extended axis, you see a red dot, which represents the electron. And the task at hand here, of course, is to bring the two charges together. Now, this situation is not as simple, of course, as the standard freshman physics problem, because we've got these collapse dimensions to also consider. So I've drawn one of those in, going through the center of the proton. We are looking at a two-dimensional cross-section of something going on in nine-dimensional space. So we have to address the somewhat awkward question of just what does that proton look like in all of its nine-dimensional glory? The answer is, I don't know. It could be spherical, though I tend to doubt that. More likely it's got some kind of texture to it. Perhaps it's spiky like a sea urchin. Perhaps it's got long graceful arms like a spiral nebula. But the point is, as we bring the electron in toward the proton, we may have mechanical interferences that we have to consider. And so I've depicted that here by adding this blue wavy line. When you're far off to the left, the electron obviously can come in along the straight line, along the extended axis. But as we move in closer, it may be that there's actual interference that goes on. The wavy line, in other words, is the best we can do. So, let's bring the electron to the proton. Here, the electron is passing over some interference. Note that it has to push out into collapsed space to do this. And this is not a stable situation for the electron because it's storing energy in the collapsed space. Here, the electron is back on the extended axis, and so that's better. But ultimately, of course, the electron wants to end up at a point where the electrostatic energy is at a minimum, and the energy stored in collapsed space is also at a minimum. So in our diagram, this is where it'll end up. Notice what's happened here. We've quite naturally arrived at a situation where the electron has a lowest energy ground state and some number of higher level quasi-stable states. The atom is exhibiting quantized energy levels. Let's explore how we might expect such an atom to behave. First, it's easy to envision that thermal agitation of the atom might impart to the electron enough energy to promote it to one of the higher quasi-stable positions, where it may linger, and then, because of electrostatic forces, eventually fall back to the ground position. Note what happens when this occurs. The collapsed space has to be stretched open and then released. And as you would expect of any such elastic media, when it's stretched and released, a wave will emanate outward. In a moment, I'm going to argue that the wave won't dissipate in all directions like you might expect, but rather remain as a packet and be channeled along the dimensions of extended space. But for the moment, let's just assume that that's correct and see where this takes us. So what happens if such a bundle of energy, such a photon, for clearly that's what we're talking about, strikes another similar atom? Well, the amount of energy contained in that photon is exactly the amount necessary to stretch open collapsed space and allow one of the ground state electrons in that atom to be elevated to a higher energy state, where it'll remain for a few moments and then fall back to the ground state. So clearly this model supports the emission and absorption of photons, but we can take it a step further than that. Suppose we have a material that has a particularly large energy barrier between its ground state and its first elevated state. That means that an electron will have more difficulty getting into that elevated state, but it will also have more difficulty falling back to its ground state. And that'll make this elevated state a quasi-stable one. So we could now imagine a material that has many such atoms with their electrons in this elevated state. Eventually, one of the atoms will release its energy, the electron will fall back to the ground state, and a photon will be emitted. That photon, when it strikes another atom, also in its elevated state, will have exactly enough energy to stretch open that collapsed space and release its energy from the second photon. And note that when it does so, it will do so in an exactly zero-phase relationship. In other words, the two photons will be coherent with each other. So this model also supports the stimulated emissions that are at the heart of laser operation. Okay, we've seen how photons are produced in this model, but now let's take a closer look at the photons themselves. Recall this diagram from earlier in the presentation and direct your attention to the bottom portion of the picture. Here I'm depicting how two collapsed dimensions are embedded into each point along any extended line. And we've seen how a photon is created when an electron transitions between two energy states in an atom. And in order to do so, the collapsed space is stretched open and released. So what would we expect to happen? Well, I've tried to illustrate that here with this little diagram. As the disturbance occurs, we get two wavefronts propagating out in opposite directions from the point of disturbance. Notice how the energy of the disturbance is trapped by collapsed space. Rather than dissipating outward in all directions, it's contained by collapsed space and propagates as two mirrored bundles. It's like setting off a firecracker inside a long pipe. You get two wavefronts traveling in opposite directions. Yet when we create a photon via electron transition in an atom, we don't see two photons, we see only one photon. Why is this? Well, consider the geometry of the situation. We know that thermally generated photons have wavelengths that range from a few hundred nanometers to a few thousand nanometers. Yet we can assume that the electron transitions that we're talking about here occur within a fraction of a nanometer away from the nucleus. So it's not as if you're setting off a firecracker in the middle of a long pipe, but more like setting it off right near the capped end of a pipe. One portion of the disturbance is immediately reflected off the cap, and that adds to the portion of the disturbance that's outbound. In support of this idea, let me say that there are other means of generating photons besides state transitions. For instance, if you collide an electron with a positron, they will annihilate each other, with the result being a mirrored pair of gamma-ray photons, just as predicted here. So just what properties might we expect of these photons? Well, as we've seen, they consist of a disturbance in collapsed space that propagates along a line in extended space. Yet until just now, we've known nothing of collapsed space. So to us, we would only observe where they exist in extended space. In other words, we would observe them only where their fronts pass through extended space. Thus, they would appear to us to be point particles, just like electrons. And yet, as we've seen, they really are wave phenomena. So we would expect them to have all of the standard phenomenon that you associate with waves. That is to say, reflection, refraction, diffraction, and so forth. So taking these last 2 points together, we would expect photons to exhibit this strange sort of wave-particle duality. Next, notice that they have no mass associated with them. Photons don't have, it's not a mass that's moving through space, it's a wavefront that's moving through space. So how fast would they propagate? Well, as in other such situations, that depends on the elasticity of the media they're moving through. So in this case, the velocity would be determined by the stretchiness of collapsed space. And we have a name for that, and that would be the impedance of free space. Is there anything else we could know about these photons? Well, yes, there is. We know from Maxwell's equations that a photon consists of an electric field and a magnetic field passing energy back and forth between each other. How could we harmonize that view with the one that we've come up with here, namely that a photon consists of a distortion of collapsed space that's traveling along a line in extended space? Well, we could do that if we made the assumption that an electric field and a magnetic field were simply two different ways of distorting collapsed space. So let's proceed down this path and see where it takes us. Let's make the assumption that an electric field is some kind of stretch of collapsed space, while a magnetic field is some kind of a twist in collapsed space. Let's explore the magnetic case first. So if we're going to assume that a magnetic field is a twist of collapsed space, then in the case of a horseshoe magnet, it must be that there is a static twist trapped between the two poles. How would this manifest itself? Here I've depicted a horseshoe magnet, and the two bent arrows in the middle there are supposed to represent the twist of the collapsed space between the poles. So what happens now if we were to bring two of these magnets together such that like poles are together with like poles? Well, as the twisted space of one magnet begins to overlap the twisted space of the other magnet, the overall twist, the combined twist of the two, is increasing. And this is going to require energy because collapsed space does not like to be distorted. And so I would predict from this that the two magnets will repel each other. Conversely, if we flip one of the magnets over so that we're bringing opposite poles together, as the magnetic field of one overlaps the magnetic field of the other, the twists will tend to cancel each other. This would be a lower energy state, and I predict that the two magnets would attract each other. Is there any other test we could do? Well, yes, it turns out that in our arsenal of particles now, we have the electron, which we have postulated has all of its volume in collapsed space. What happens if we were to fire electrons into this twisted space between the poles of the magnet? Well, as you would expect, the electrons would tend to follow along the twist of the space and be bent. There's one other thing I'd like to say about magnetic fields in this model. Note that this model does not support the idea of a magnetic monopole. For just as it's impossible to wring out a towel with one hand, it would be impossible in this model to maintain a static twist in collapsed space with a single pole. Turning our attention now to electric fields, we've postulated that an electric field is associated with a stretch in collapsed space. But clearly it's more complicated than this, since electric charges have polarity associated with them. In this diagram, I've shown a line in an extended space in blue. It's speckled with evenly spaced red dots, which are supposed to represent points in collapsed space. The idea is that the uniform distribution of red dots represents a situation with no electric field. If there were a field present, the density of points would be locally altered, as shown in one of these two cases. Now, I'm not prepared to say which configuration corresponds to which charge, but clearly bringing the two blue lines together would tend to neutralize the distortion of collapsed space. Since it takes energy to distort collapsed space, bringing the lines together would represent a lower energy configuration. The opposite charges, therefore, would experience an attractive force. Likewise, bringing similar charges together would enhance the overall distortion of collapsed space. This would cost energy, and so the charges would repel each other. In all candor, this part of the model seems a bit weak to me. I would feel much more comfortable if it was obvious that a charge moving through space would inherently create a magnetic field and vice versa. But nonetheless, the picture seems close but not spot on. Anyway, let's turn our attention to another topic. Consider any of the basic particles, electron, proton, neutron, that we've talked about. In all these cases, we've said that they have some or all of their volume in collapsed space, and hence collapsed space is stretched open to accommodate them, and therefore there's this energy content that's inherent in the particle. Assume that this black dot is one of these particles, and it's located at some fixed point in extended space. Let's say that the energy content trapped in the stretch of collapsed space is E. We would certainly expect that it would have exactly the same energy content if it were moved to some other fixed point in extended space. After all, it would be stretching some other region of collapsed space, but the amount of stretch would be the same as before. Now suppose that the particle is moving through extended space at some constant velocity. Whatever energy content the particle has should be constant from moment to moment. In this case, new regions of collapsed space are being stretched open at exactly the same rate that previous regions are allowed to close up. There's no net loss or gain in trapped energy. Things get more interesting if we try accelerating the particle. Now you are essentially opening new space at a faster rate than the old space is closing up. It requires additional energy to do this. In other words, the particle will resist being accelerated. It will appear to have mass. Likewise, if we try decelerating our particle, we will have to absorb energy out of our system to do so. Again, the particle will appear to resist us. Though I've stated this in rather simple-minded terms, the mechanism is essentially the same as that of the Higgs field. The Higgs field is everywhere present, and it resists motion through it. While there are many more things I could add to this model, this is probably a good place to conclude. So let me make two final remarks. First of all, when I first encountered physics back in high school, I was amazed at how many things could be expressed with just 3 types of units. After all, if you're talking about position, velocity, acceleration, energy, force, work, momentum, everything's expressible in just 3 units, meters, kilograms, and seconds. But in light of this model, that all makes sense. Meters are a measure of extended dimensions. Seconds are a measure of the time dimension. And as we just saw, kilograms, which is to say mass, is really just a measure of collapsed dimensions. 3 types of dimensions, 3 types of units. Over the years, there have been many attempts at unifying the forces and finding that common element that ties them all together. My model has much to say on this. We've seen how the ever-present compression of collapsed space may contribute to the binding of quarks together to form baryons, and to bind baryons together to form nuclei. Thus, the collapsing of space would mitigate the strong force. We've seen how distortions of collapsed space may account for electric and magnetic fields. I have only a passing knowledge of the weak force, but I'm aware that it has been shown to be essentially a special case of the electromagnetic force. In this model, all 3 of these forces appear to result from the distortion of collapsed space. Now, if you combine this with general relativity, which shows that gravitational force results from the distortion of extended space, you come to the conclusion that all of the forces are simply the result of distorted space, either extended or collapsed. Thus, this model unifies the forces. I said at the beginning of this presentation how I would show that many of the principles of quantum mechanics would simply fall naturally out of this model. So let's look at what we've seen. We've seen that this model accounts for electron localization, the Pauli exclusion principle, tunneling, the origin of quantum states, the nature of photons and how they propagate, stimulated emissions and the interaction of photons with matter, the wave-particle duality, the nature and origin of electromagnetic fields, the origin of mass and inertia. That's an impressive list, if it's true. So do I believe this model? I don't know. It has the right feel to it, but I have to leave it to someone else to build the mathematical foundation underneath it to see if it is truth. And so if you want to contact me, you may do so at mmcclure@energyaccess.com. I'm Malcolm McClure.